Okay, so I'm going to be doing a video on how to solve elastic collision problems versus inelastic collision problems. You should have had the notes on these from Tuesday. So the short idea here is that elastic collisions are collisions where things bounce off of each other. And there's no energy loss. They just bounce off of each other. And inelastic collisions are collisions where perhaps the two objects stick together or collide and then stick together. For example, maybe a car crash where the two cars collide and move together as one. Or another type of inelastic collision is where there's energy loss. For example, if you take a piece of Play-Doh and roll it into a perfect ball and drop it and it lands on the floor, when it hits the floor, the bottom's going to smush out a little bit. It's going to flatten. That means that there's energy loss during the collision because it takes energy to smush the Play-Doh. So I'll be solving one of each on this video. Let's just start with number one. We have a canoe moving to the right. So let's call this part A, or canoe A. And it's going to be a head-on collision moving to the left. So we'll call this B. This one right here, this one's moving at 12, and the other one is moving at 6 in this direction. So we're trying to figure out the velocity of the canoe after the collision. So I'm sorry, this is a raft. So this is the raft. I should be a little bit more careful here. It's not two canoes, it's a raft and a canoe. Okay. And we're trying to figure out the velocity of the canoe after the collision. So the idea here is that the momentum of a system is, initially, it has to be equal to the momentum of the system at the end, at final momentum. Assuming that there are no impulses along the way. Again, that's the same statement to saying that the total energy is equal to the total energy afterwards. Assuming that no work has been done. So it's the same idea. Here we have the initial momentum of two objects. So the initial momentum of the two objects is going to be the mass of the canoe times the velocity of the canoe plus the mass of the raft times the velocity of the raft. That's all initially. That has to equal the total momentum, the mass of the canoe times the final velocity of the canoe plus the mass of the raft times the final velocity of the raft. Right? So this is how it's going to work. This type of generalized formula is going to be how you do elastic collisions. You keep the objects separate. You keep the objects here separate because they bounce off of each other. So now it's just a matter of solving for the final velocity of the raft. So let's just plug in our values now. It's going to be 16 times 12 plus 4 times a negative 6. Again, we have to have a negative 6 here because the reference frame matters. And that's going to equal the 16. Now it says that the canoe, the canoe is what we're trying to find. I'm sorry, I had a brain fart. So we're interested in the final velocity of the canoe. Did I say that enough time? I feel like I just said that 3 times in a row. Final velocity canoe. Plus now the raft tells us that it's going to be 4 and moves to the right at 22. Okay, so we got to be a little careful here. That after the collision, this raft is now moving this way. So this is going to be a positive 22.7. Right? It matters. It matters which direction it's going. So now you can see that the only thing we don't know is the final velocity of the canoe. So yes, this is the one we were looking for. So now it's just a matter of plugging into a calculator. So 16 times 12 minus 24. Subtract off the 4 times 22.7. Divide by 16. I get 4.825, so 4.83. So 4.83 meters per second. And now that's going to be to the right because it's a positive value. So that's the velocity of the canoe afterwards. That's how we do it in an elastic collision. Let's do an inelastic collision. Now let's take a look at number 3. Here we have a 1,500 kilogram car traveling at 15 meters per second to the south. It collides with a truck that is at rest, and then they stick together. So I'm just going to draw it like this. I don't need to draw it south. I mean, if I wanted to, I could always say, hey, here's my compass, and south goes this way, right? I could do it that way if I wanted to, but that's a little silly. The physics here is this. We have a car going this way, and it's going to hit something at rest. And they're going to entangle, they're going to stick together and move together as one, right? So let's just call this A and call this B. So the way we're going to do this, again, is we have to start with the initial momentum of the system. It has to equal the final momentum of the system. The initial momentum of the system is made up of these two objects, just like before. So it's going to be MAVA plus MBVB. Now here is the kicker. If they stick to, if they stick together, that means that they are functioning as one object with one velocity because they're stuck together, they travel together. So the difference between a formula like this up here for elastic collisions is going to look a little bit different now for inelastic collisions because the objects stick together. So they have one combined mass and they travel together at one velocity. So this right here is the main difference on how you calculate inelastic collisions. So it's going to be 1,500 times 15 plus 4,500 times 0. All right, this thing was at rest, so that's why it's 0. That has to equal 1,500 plus 4,500, and then they have that one combined velocity. So it looks like all of the momentum of the system comes from the car that was moving. So 1,500 times 15. And divide that by 6,000. 3.75. So the final velocity is 3.75 meters per second. And that's how that's right there, they stick and travel together at 3.75 meters per second. And that's how you do an inelastic collision.